last time we are on the step and for the tokenization and a lot of things. Let's actually go back to the fundamental to talk about. I'm sorry, okay? We have a whiteboard. Okay, so here this year I teach this data structure in totally different way. Okay, last year I think that Helen know that I follow the chapter by the textbook, but I don't think that's a good idea. Okay, because we have the new need for AI and computer science need. Okay, so basically, I think the traditional way to teach the data structure is not enough or not the right way to teach it anymore. Okay, so we kind of change our way of teaching. So this year we are basically based on a topic. Okay, based on a topic. So first topic we pick is the hash table. So we talk about hash table and go over the algorithm for hash table and how to build hash table and how to use hash table and the efficiency of the hash table. Okay, we did not go into the very deeply into different kind of hash table, like in this type of hash table or using the double hash hash table. That actually is technical detail, and those technical detail usually you search for the ChatGPT, you can get it nowadays. Okay, so that's not a key point. Key point is, do you know about the nature of the computing or not? That the topic is more important. Okay, topic is more important. So then second topic we pick is tokenization. So tokenization, we talk about you have some text, right? So it may be in certain language. You need to translate that language into another language. For example, you translate your C language, C double plus language into machine code. That's one important thing. Or you actually have the 2+3 number and you want to get the result. You want to convert it into PostScript and then evaluate the PostScript and you get the result, right? So basically, here you have some sort of text, and here you have grammar, and you use grammar to build a machine, a translator. So use the grammar to actually take in your input to translate it to machine code or to PostScript, Postfix evaluation form. So you can evaluate on it. So this part actually is the topic of the tokenization and then parsing and then compilation. And this is actually currently the most important topic in computer science. It's called this portion. The grammar is related to programming language. There is a course called programming language. The translation part here is actually is the topic of a compiler. Okay, and this programming and compiler actually is a core and computation for AI. AI based on you have some sort of input. It may be text, maybe image, but you kind of translate it into some sort of the computing values. So you can output it to a certain format. So you can output, so you have an image input, you may have an output of the image. The output image maybe is some sort of recovered image, okay, recovered image or some sort of enhanced image, okay. And then you can have the text and text translate to image, okay. So basically, you can just think about text is a language, image is also a language. You can translate image to text, text image to image, or image to image, or text to text. Okay, that's a whole process of the compilation. translation. Okay, translation. So during the translation, you base on some sort of grammar. The grammar is the English language grammar or visions label on the car, and you recognize the car and car. You have the distance calculation. Those kind of things is the grammar for image. And those image and language grammar, okay, basically build a language model. So language model is built upon those grammars. You have the grammar, and then you have everything, then that become language model. Okay, so this one, let me take a picture for you. So I'm going to go into the detail of more about the large language model. So why large language model right now is so popular is that large language model has a lot of parameters. So let's clean this one again. Okay, let's clean it. So basically, again, you have some input. That's your input. So your input can be certain language. Let's say it's actually English. It can be image. It can be Chinese. It can be a graph. Okay, anything. So you want to translate it to different thing, and or you do a ChatGPT to generate some new text. That process actually is a process of translation. Okay, so translation actually is the purpose of the compiler. And at the end, you get some result. The result is a different language. So this different language can be Chinese, can be a update for image. And then during this transformation, you're doing that grammar. Okay, I talked about this already. So which grammar is actually most appropriate? You have to evaluate. So right now, for example, my input text can be I love you, right? It can be I love you. So I love you actually, it might fit into subject, verb, object, right? Okay, then that one grammar rule is subject, verb, object. It can be subject, verb, object one, object two. I give you a present. So that's actually can be that grammar. So the grammar, there are a lot of different kind of grammar there. And you will evaluate which one is the most closer grammar. Okay. And then based on that, you may find out this SVO is the closest grammar it is. And that S is subject. But this I, you can actually further categorize this I into maybe it can be a male, can be a female, can be an animal, can be a lot of things that can log. But you evaluate, maybe there's a car, a nouns that is car, even it's a SVO model. But if you have a car that loves something that's impossible, because car have no emotion, car actually doesn't show affection. Actually, car doesn't actually love anybody. So that actually, in a way, car it is categorized as a car that's actually almost like impossible. So based on the evaluation of those score, you can determine whether this one is a male, female, or an animal, or something that has the capability to love. If it's some sort of a category that cannot log, that will not be able to basically that cannot actually do log. Okay, so based on that, you actually find appropriate set of the unit, and then the next one you actually go to see like build a knowledge net. So knowledge net means that you have some sort of male love female, female love male, and these two maybe become twin inference, and it may actually go to marriage. Okay, so you can actually create a concept called marriage. If male love female, female love male, both happen, and then that may indicate a marriage. Okay, something like that, then you can do some sort of reasoning. So basically, tokenization, let me go back. Tokenization actually is the starting scenes for the whole thing if you want to do translation. Okay, if you want to do translation. And then this is actually the overall topic of this language translation. Okay, and we teach you data structure based on the topic. And based on this topic, so far, okay, let's go back to this language translation topic. Based on this topic, so far, we introduce two data structure. The first data structure we use is Q. Okay, the first data structure that we use is Q. So the Q is used when we have the first in, first out. When we actually initially doing the tokenization, making sure that you actually a later is tokenized, and then feed that into some sort of finite state machine. So finite state machine is not data structure, it's a program structure. So we introduce the first program structure there. And then you create a vector of tokens. So we also introduce the tokens vector. And then vector of tokens that is actually being translated to fully parenthesized string. So there's a fully parenthesized string to put more parentheses in there. So this one actually is with the help of the stack. Okay, so Q vector stack in last year when we teach you the basic data structure for user code, all of you already learned it in Java, right? So we don't actually repeat what they are. But here you do see them all show up to help to do processing. So the first one we teach you using finite state machine to help tokenization, categorize the different token into numbers and maybe parentheses. Okay, those kind of things. Second, you use a vector and then also the step to do fully parenthesized from this one is working on infix token string into fully parenthesized. Okay, and then it's a fully parenthesized fully parenthesized string being again converted to Postfix. Okay, and Postfix also is in a vector. Okay, so we are up to there. Okay, we are up to there. Last time we are up to there. Okay. So today we are going to continue. We are going to continue from there. We are actually next step is that we will base on a Postfix vector. So you may have 2, 3 plus 4, 5 plus star. Now you need to actually evaluate to certain value. So And when you do evaluate, you need to recursively pop this one out. That's actually a star. Pop this one out. That's your right operator. Pop this one out. That's your left operand. So you evaluate this one and this one first. So this 4 and 5, you pop out 4 and 5, and you have right and left. You evaluate this one. If there's nothing you can pop out, you evaluate and you will get something like 9. You push back the 9 to the stack. And then this one, you have 2, 3 plus, you push back 5 to the stack. And then you have the star with the 5 and 9, and then you pop out the whole thing, you evaluate it back to 45. So when you stack being pop out and push back, pop out and push back until you only have a 45. That is your final value that you want to have. Okay, that's the final value that you want to have. So that's the algorithm we will be using. Okay, that will be the algorithm we will be using. So basically, we use the topic to talk about the different data structure and use the data structure to solve the problem. And then during the computation, we may use several data structures, several algorithms to finish the computation. Okay, this is topic-driven data structure teaching right now. Okay, I'm trying to actually make sure that I try to change our way of teaching data structure into this kind of topic-based. Okay, in the past we just go to teach you what's stack, what's queue, how they can be used. Okay, but that's not enough to solve the problem in future world. Okay, so basically, one more thing. So basically, the computer science, okay, every one of you will eventually go to college. So the computer science is like this: you learn basic language. Okay, so far we teach you 4+ language, and then second level you teach you data structure and algorithm. And data structure you learn queue, you learn a stack, you learn a tree, okay, and you learn maybe graph, okay. Okay, it's different things, and you learn tons of different kind of programming paradigms, such as dynamic programming, and then you learn maybe divide and conquer. You learn all kind of things. Okay, so that's called data structure and algorithm. And at the same time, you also learn some sort of discrete math. Discrete math is very close to data structure. Data structure actually more for the data and more for CS. Discrete math more for problem solving. So this, if you haven't learned this, you probably need to take it in high school because that will help you in terms of if you go for a competitive programming, okay, in user code, those kind of things. Nowadays, they need a lot of discrete math knowledge. They just don't tell you, okay? Pure coding is not enough. Okay, and then you move on to the next level. You do learn what is programming language. Okay, this is actually not a programming language that you first know. That's the only language right here. You learn finite state machine. You learn so-called regular expression. You learn actually context-free grammar. Okay, different things that related to grammar and the language. Okay, how to translate it, how to use them to build large language model. Okay, and then that's one topic, very important. Second one is you need to know operation system. What is OS? What is queue? What is a hash table? What is hash memory? what is cache memory, how to parallelize program, how to combine multi-programming back to one program. Okay, that's very important operation system that manage the task and memory. Third one, you also need to learn networking. Okay, and then you also need to learn AI. AI is the tokenization, okay, building large language model, apply statistic to do reasoning, and then getting the reasoning result, and then apply them to generate a new language. Okay, that's the AI part. And then you also need to learn 5 database. You also need to learn database. Okay, so far, okay, let's see. These are primarily different topics. So these are the core courses for CS. No matter what major you go in, you go to college, you still need to take these different courses. Right now, we are teaching you these, the DSA course, but eventually you need to go to college to take all of these different courses. So right now, we try to help you to have an overall view of where your computer science education should go to, okay? And once you have this, everything you have, the programming language, operation system, networking, parallel processing, and also AI, okay, also database, this kind of knowledge you have enough, then you are ready to become a back-end engineer. And you may also go for front-end engineer, then you can go for a job and accumulate more knowledge. Okay, so that actually you go for internship, that's that direction. So our core right now is helping you to build up the intermediate level of your knowledge in computer science, okay? And that's also related to usable competition, but I do not emphasize usable competition right now because eventually you will get some sort of award there, but that's not a goal. The goal is you need to know about how to use a data structure and algorithm and apply them into the computer science study, okay? And then nowadays, those algorithm and data structure and even the whole competition for user code basically can all be replaced by what? By ChatGPT. ChatGPT can generate a better code for you. Okay, so our goal is not to just learn the coding part or language part. Our goal is must give you the best idea of what the CS core is, what kind of the real world problem is, and then help you to organize your DSA and your programming language to support those computer science study. Okay, is that okay? Because these different lower end part, they are always can be solved by ChatGPT now. So the value of computer science will get lower if you just know about the data structure. That's not enough. Even though that still be very hard, okay? Even though it's still very, very hard. And even though that still, I would still strongly suggest every student to go through the hardest way to train yourself, okay, in that domain. Okay, anyway, that's actually where we are right now. So let's actually go back to today's topic that we will do Postfix evaluation. Okay, so that here, right here, you can see that that actually is in a Python course. I translate to C++, but I haven't finished that. In the past few years, I do teach C++ programming, but I never have the chance to save the program into the PowerPoint. Okay, I tried, but I was sick for 2 years. So I went to hospital, so I do not have the time to finish that. Okay, so this time let's go to, we finished the in-fix to Postfix. There are 2 methods. We introduce you 1 method, okay? And then next one is Postfix evaluation. We are going to get started from here, okay? So here, this one is the final stack example. So stack we use many times in this whole tokenization one. This one is the last topic for stack. We will consider the evaluation of expression that is already in Postfix format. So you have the fully parenthesized infix, and then you translate into Postfix without parentheses. At this time, Postfix, you do not need any parentheses. And then it's actually a stack is again the data structure for the choice. Okay, data structure. However, you can scan the Postfix expression. You actually have a stack. You have plus time 6 by 4. So 6 by time, this is one thing. So you pop out this, and this one's process and go back with 30 there. And then that's actually the second operand. And then you pop out this as the first operand. And then this is 3 sum together. Okay, then you got the result. So that's the way you would do it. Okay. And then in this case, the next symbol is another operand. Okay. So before push it and check the symbol, now we use the star as operand. That means that 2 most recent operand will be used. So you continue to look for 2 operand. By popping out step twice, we get 2 operand. Then that 2 operand is for the second operator star. We get to 30. Then the 30 is the second operand for the plus. And then now we actually push back to the start so it can be used for as an operand later. Okay. Okay. So the process of this is that you push in 4, you push in 5. Okay. Actually, you may have fully parentheses. I'm sorry, I made a mistake. The fully parenthesized expression might be this. Okay, so you push in 4, then you actually push in 5, and then you push in 6, and you push in star, and you push in plus. So you pop out your plus, you pop out another one, a star, and then you actually pop out 6 and 5, and then these two you combine, you push in 30. And then 30 is a operand for this. So you pop out 30 and then use plus and power 4 to do plus, and then you push in 34. And the end result in the step will be what you want to have. Okay. So that's actually the algorithm that would actually work. Okay. So I don't go through this one anymore. Okay, so that's actually the algorithm here. So we can create a open stack called open. We can create a so basically you right now you still have 2 different stack. One is operand stack, one is operator stack. Okay. One is operand stack, one is operator stack. So basically you kind of okay, so you would so from Postfix. So the Postfix is like this. You open your operand step and your token list. Okay, you have your token list. So from your token list, so this token list should have your 4, 5, 6 time plus. Okay, that actually is your token list, and it do split. Okay, no, it's okay. We no longer need the split part. Okay, the result that we get from the vector from the fully parenthesized Oh yeah, we still need to actually do I'm sorry, you already postfix. So that postfix you do not need to do split. Okay, you don't need to do split. Okay, we'll check. Okay, if it actually is a string, we'll split it. Okay, anyway. Now anyway, if you find there is a token, that token is in this number. Okay, it's a number. Then you push in the number into the step. Okay. If it is not a number, that would be a operator. So your operand will pop out two number. You would pop out two number. Okay. Then you would do math. Do math is using the token. So this token right now maybe is plus. Okay. Then you would actually do the operation. And then you push in your result again. Okay. And then when you actually finish everything from your operand, that's the final number in your operand stack. That is the value you will actually pop out. Okay, that's all. That's all you need to have. Okay, do math is to evaluate, do math part is to evaluate your math. Okay, you can put in as many operation that you can have. Okay, so you can do this one. It's a full string, and then based on this evaluation, you get a result. Okay, you get a result. Okay, let's actually translate this one to our program. Okay. So last time we are on here. I will copy everything that I have. Let's continue using this 0.5, okay, since the environment is right here. So let's continue use this environment. Don't create a new, don't create a, don't create a new folder because we may ask for trouble, okay. Okay, let's actually, okay, so right here, we can code. So last time we finished the infix to postfix. Okay, so this infix to postfix, we are here, okay. And I fixed the bugs, okay. Last time, finally, I keep doing debugging for infix and postfix. Actually, there is no bug, okay. Actually, no bug. The only thing happen is that I do compilation, but the compile code is holding my executable. So whenever I compile to the executable, that program is not stopped. Okay, it's not stopped. So actually, I cannot compile to the new code. So what happened is that I will need to recompile it, okay, to a new function, then it works. Okay, anyway, that's not a problem. So today we'll continue from here. So I'm not going to use this infix to Postfix. I'm going to copy it to a new program. So this new program, I'm going to change the name. I'll call it calculator. So because we finished so many steps, we are go down to the last step, last step. Okay, so here it actually, okay, it is a string. It is a string, no problem. It is a string. So here, next one, we are going to do step 5. Okay, this step 5 is actually called convert the postfix. Okay, not convert, actually to evaluation of the Postfix equation. Okay. So what we want to have is we need to have a value of, let's assume it's double. Okay. Equals calculate. Okay. Calculate what? Your Postfix expression. Okay. And then you will see out result value. This one, let's call it value. Let's call it final value. Okay. So that's the program for calculate. So here we will need to have a program that do calculate. And you return double value. Okay. And you get a string. Let's use alias. Okay, to save space. That's actually you get the Postfix expression input. Okay. Now right here, going back, you will need to have one operand stack and you need to split them into tokens. Okay, Postfix, you need to split them into tokens. So let's go back to the tokenization part. Here you get expression, and then you do fully parenthesized. Okay, so after parentheses, you do tokenization. So we do have a tokenized function. So let's do this. Let's put it over here, okay? Let's create a vector of token. So here, in order to make it, to have it as a difference, so let's actually make it as the Postfix tokens, P tokens, okay? So P tokens, and based on your Postfix description, so you get the Postfix string. Okay, that's not a problem. So right here, let's do this. Let's return 0.0. Okay, so that calculator will get some sort of result. But right here, what we want to do is that we want to see every token. So let's do for string. Okay, token from P tokens. Okay, let's do this. See out token. Enter. Okay, we just do this. So we would see the result for tokenization. Let's do this. Let's do use P token. Okay, so that would be the Postfix tokens. Let's get out. Okay, right here in here, let's do G double plus later that CBE SO later. Okay, then later 4 plus, let's do this, let's do 4 plus 5 times 6. Okay, so 4 plus 5 times 6, we got fully parenthesized. We got the tokens in fully parenthesized, okay. And we got the tokens, and we got a postscript description, and the postscription get the P tokens, and the final result 0. Okay, that's actually so far so good, it's actually correct, okay. And then this one not needed, we will comment it out. This one is just to give you the testing, making sure so far your programming is correct, okay. So that's actually delete them. Comment it now, okay, comment it now. And then we need a step of step for the operand step. So let's do vector of double this operand step. Okay, let's do this. Okay. So we do create an operand step. Now this one is actually deleted. We don't need it. Okay. And then we will translate this whole thing. So eventually we are going to do operand step the pop. Okay, so let's do finally we will do operand step the pop. The last value stored in it will be pop. Okay. For sure. Okay, I'm sorry. It's not vector. This one should be step. Okay. Return value type does not match it. Okay, it's not here. It's actually not the pop don't have return value. You should use top function. Okay, I'm sorry. So that's a top value you need to return. So that's that. And then we go to here. So let's copy this algorithm for reference. We will translate it into C++ format. Let's put it over here, okay? It's not far away, so. No, it's actually not going to help. You still need to translate. Let's just put it here, okay? So now next one, it will go into the process of, okay, let's do it. It's very simple, so we do not need to do differently. So it has the token from the P tokens. Okay, we do this. Then you have if something else something. Okay. If something right here, you actually do token is a number test. Okay. So token is a number test. We do have that. Okay. We already had that. That is not needed to redo. That actually go for as a search for it. Here tokenization. There's a function called fully parenthesized. So that one is a remix. There's a remix this is the operator, and then there's a function called is operator. We have a Remax. Okay, we actually use a Remax to check the number and the ID. Okay, so we just need to check it. Let's see. Let's actually, in this case, let's try to find. Okay, try to find rejects. Okay, we should be able to find where the it is used. So right here, you check if its number is this one is if number. Okay, this one check the token if it is number. So let's copy this one. Okay, down to here if it's the tokens is a number. Here you only have the number and okay. So let's do this. Okay, let's actually right here. Okay, let's put a remark. Sometimes you may have ID, but like ID, you can translate it to number. Right now, we don't do it, okay? We don't do it because we don't have a storage of variables. But let's put here, okay? So let's put a remark over here. Okay. So you can write down some notes right here, okay? For future expansion, you may convert a value, a vector, a variable as ID type into a number, okay? But anyway, that's one thing you can do, and you can bypass here. So anyway, right here, we are assuming that this actually, you kind of check if the expression is a number, okay? If it's a number, we will convert it to, evaluate it to a double value, okay? So the number, the token will be, so right here, we double plus convert a string to a double. So using the string to double function right here, okay? Let's copy this one, okay? So basically, you convert your using string to double for your token. No, it's a little bit too complicated, okay? This one a little bit too complicated. Position is side T. Let's use a simple one. Let me see. Actually, let's use A to OF function. Okay. Let's just use A to OF function. This one a little bit too complicated. So you do A to OF, you have a string. You do A to OF, okay? Let's change it. Okay, so this one, let's call it, yes, let's call it none, that's fine, okay? A to OF, so you actually convert your token that to C string. Let me see. So here you actually have a C double plus string. So you actually do C double plus string to C string. Okay, the function is called C underline str. So it's actually C underline str. So this one convert from C double plus string to a C format string, and you convert it to double format, and you got a number. That's it. Okay, that's actually good. Okay, so this one, let's close it. We no longer need the search. Come back to here. So that one finish it, and then we will push it to the operand stack. Okay. So push it to the operand stack. So operand stack that push your num. Okay. So that's finished. Now we do the else part. The else part, let's copy it over. There are only 4 operands, so no problem. Okay. Okay, so let's do double operand 2 that actually is from the top. And then your operand stack that pop. Okay, there's 2 operations needed. So it is the operand stack pop being assigned to operand 2, and then you pop. So this is whole thing. You do it one more time. You put it to operand 1. Then the operand 1, you finished this one not needed. Okay, finally, you do have double without do mass. The token, do mass, and eventually your operand stack will push the result. Okay, that's actually what it is. Now we need a function called do mass. So let's put the do mass on top of the mass here. So it will have a double value do mass. Okay. And here you should get a string of the alias operator, and then double. Actually, let's call it data 1 and double data 2. Okay, so that's what we need to have. What's wrong? This one should be lowercase s. Okay, so we do that. Then we need to have an if statement. Go to the do math. So we do if statement, else if, and do these 4 different things. Okay, so we do. Okay, so this one we can copy for 4 times. If nothing happens, we are going to return 0. This is to help the compiler to avoid the compilation error. Okay, so this one you do minus time division. Okay, so that actually finish it. Let's actually check one more time, because let's actually go back to the when we provide the operand, we have the number ID, but okay, we don't have modulation. So the operator, we do not include operation. So if we want to do the so-called modular, we can add right here. Okay, we can add it right there. I think that's enough. We should be able to test. Okay, we should be able to test. So let's do it one more time. So here, let's do. Oh, okay, let's run this calculator. So let's have 4 plus 5 times 6. Yeah, we got a final result. Any questions so far? No. Okay, so finally we come down to the calculator and get everything work. Okay, so this one we go through several stages, doing a lot of processing, and eventually we get it work. Just to demonstrate you the use of the stack, queue, and vector. Okay, in combine, how can we do simple language parts? But calculator is the most easiest one. There are some other issue that's postfix to infix, infix to postfix, infix to postfix to infix, prefix to infix. There are tons of other expression conversion algorithm, but we don't want to waste our time on here. Okay. So that's it for this algebraic thing. Now we are going back to our new topic. So here we kind of finish. Here we kind of finish the so-called stack portion. Let's see. Where we actually finished the infix postfix part. Okay, we are done with this one. So right here, this one, I think we finished this chapter as well. So chapter 3, we finished 2 easy recursion. We talked about it before. We don't need searching and hashing. We finished. Sorting. Okay, there are tons of other sorting algorithms, but right now these are not top priority. So we kind of don't need that. Next one, we are going to tree and the tree algorithm, okay? And because we will have spent some time on parsing tree, okay? Parsing tree is to help you to do grammar search. So this is more important part to go into the tree, okay? So today, let's get started with the basic idea of tree. So we actually studied tree in the Java part, but let's do it. Okay, let's see. Let me see if I do have a C double plus node. I think I have. So let me create new one. So right here, C double plus part, I'm going to create a new topic. This one is called 063. Tree is our new topic. So before we go to the parsing tree, what I want to do maybe is the dictionary tree. Okay, dictionary tree. So we may go over Huffman encoding. We may go over Huffman encoding. We may go to try. Okay, this different topic for this one. So let's call it this new topic. Let's not call it a tree. Let's call it a new different way. Okay, because tree everyone knows. So let's call it dictionary tree. This dictionary tree will have two meanings. One is a Huffman encoder. And Huffman encoder is actually what we talk about. It is called it actually is called codebook. Okay, so when you do codebook, actually this Huffman encoding is openly seen in the data structure course as a homework. Okay, as a homework, and then that actually is widely used in the codebook. Okay, in the codebook when you do communication stuff. And then we may also use try. Try is a tree that used for hash table. Okay, so we may focus on these two things to talk about dictionary tree, but we'll get to there. Before we get to there, we need to study the tree again, making sure the basic idea of the tree, everyone understand it. Okay, so before that, let's actually, let me go to my C course, C level plus course. Data structure right here. Let me see, do I have let's actually look at, okay, let's follow the order. So the first one, recurrence relations. Okay, let's go over this chapter. This chapter actually not very difficult, but basically this one talk about tree beta. Okay, in terms of topic, it's a good topic talking. It involves the data structure and also involve the so-called program structure. Okay, so tree in a way is a concept. it can be a data structure. So it can be a data structure. You do have some sort of data stored in tree. Okay, that is called data tree. You may have a data tree. You may also have something called evaluation tree. Evaluation tree is not a data tree. It is a program calling tree. So you may have F2 calling F4 and F3, and your F3 calling F5 and F6. So this is called a calling tree. Okay, calling tree is an evaluation tree, and you may have a tree of the evaluation tree, and also may have a data tree. So which kind of tree you used? It depends. It depends. You may have a data tree, but your algorithm is actually linear, saving time. That's possible. You may have an evaluation tree, but you end up getting a exponential growth operation that may waste your time. So basically, how to use them actually correctly, that actually is based on the recurrence relationship. Recurrent relationship is actually how your data or your program that defined by some subcases. It's different from recursive function. Recursive function is a function calling function, right? A function calling function. Here, it recursive expression including A2 equals A1 plus A0. So this recurrence happen on the data. It's the data structure. Okay, it actually is a data structure. Data structure or program structure, they both may have recurrence relations. So here is the conceptual discussion of the recurrence structure. And the recurrence structure is the basis for the tree. You may have program evaluation tree, or you may have the data tree, okay, different kind of tree. Any questions so far?
No.
No? So now we need to try to understand the complex problem. So usually tree is in the gold division or U circle, or some silver division, but silver division usually won't involve dynamic programming. Okay, if they involve dynamic programming or something like that, it actually is in U circle gold division. They may have easy tree. Silver division usually is just depth first search or breadth first search. Okay, anyway, but nowadays we don't know. Nowadays U circle become harder and harder. They may push the original gold problem to silver. Okay, but anyway, to understand the complex problem that may otherwise difficult to solve without the recursion, okay, to learn the formulate program recursively, this program, okay, it's not just the data. To understand the three laws of the recursion, so basically right here, we are also reviewing the recursive, okay? To understand recursion as a form of iteration, okay, this is very important, how to serialize them to make it work. Okay, so you do in recursive call, if the recursive call is exponential growth, you are kind of not solving the problem. So how to get your program that you can iteratively solving it using iterator or using serialization or some sort of conversion. That's the key for this solving the problem here, okay? So what is recursion? Recursion is the method of solving problem that involve breaking the problem from bigger problem to smaller problems, okay? Okay, the sum of vector, I think this one everybody know, okay? Your serial solution and recursive solution, that's fine. So this part, we don't waste our time, okay? And we already know how to evaluate the the program, the expression, algebraic expression with the parentheses, so it's okay. We kind of skip it. Three law of the recursion. So like a robot of Asimov, the recursive algorithm must obey three law. It must have a base case. It must change its state and move forward to the base case. Okay, you must have a termination condition, and you eventually must go to the termination condition. And the recursive program may call itself recursively. So these are three laws for recursion. This everybody knows it's okay. So that actually is okay. This one okay. Step frame, I think we know what step frame is. This one is step frame or call frame. Okay, that we actually can also skip this part. Power or Hanoi, we talk about it in AP, so this one not important. Let's go. Explosion of the maze. Explosion of maze is a 2D problem, but sometimes you can do recursively. So this one, exploring the 2D maze is considered to be a program evaluation tree, recursive evaluation tree problem, okay? So you may go each different paths to continue, okay? So this one we don't waste our time, okay? So basically you have a maze, and then you want to find out where you can go out, okay? So you basically recursively searching the neighborhood, which one I can go, which one I can go, which one I can go, something like that, okay? And until this is your starting point, and until you actually get out. Okay, whatever, that is it, okay. So you just need to know it, okay? I think writing this program is not hard, so. Next one, the dynamic programming, okay? So dynamic programming in computer science is written to optimize value. Right here, we don't do coding for dynamic programming. We just want to introduce the idea of dynamic programming, okay? We just want to introduce the idea for dynamic programming, and later we will go into tree to visit the Huffman coding and the tribe, okay? So that we just go through dynamic programming. So right here, maze exploration, that is a evaluation tree problem. Okay, dynamic programming is also a evaluation tree program. Okay, heap is a data tree problem. Okay, heap. So here we are just trying to introduce to you a different way of the recursion, and that all are tree, can be program tree, can be data tree. You must know about trees application first. That's our purpose. Right now, we are still in the introduction of tree. So the evaluation tree and the data tree are two big subjects, okay? We cannot finish it in this introductory talk. We just give you example and making sure that you know that we are exploring this right now, okay? So usually dynamic tree is involved for optimization problems, okay? So optimization problem is evaluation, okay? And evaluation on a tree, program tree structure, that's evaluation tree, okay? AI is an evaluation tree. And chess is an evaluation tree. Go game is also an evaluation tree, okay? It's different tree is. So a classic problem of optimization is to make case that you actually can do optimization faster. So an easy example for this dynamic programming is that your evaluation tree for Fibonacci, okay, your evaluation for Fibonacci is actually F2 equals F1 plus F0. So if you do top-down recursion, your F5 will be equal F4 plus F3. F3 equals F2 plus F1. F4 equals F3 plus F2. So this one is traditional way to do it. You go through the recursive evaluation tree. And then if you do F3 equals F2 plus F1, you finish the smaller case and you use the smaller case to calculate the bigger case. So you can serialize it using the stored smaller values. This is called dynamic programming. That is actually the idea of dynamic programming. If you can find an optimization structure that can use dynamic programming, that you can save your time, making it from an exponential problem to a linear problem. That's the whole purpose of dynamic program. So dynamic program is a goal, it's not a solution. So when you see different problem, then it comes, how can I find a dynamic programming result? That's the problem. That's actually is the key problem, okay? Right here, I'm not teaching you, we already find all the solution for every single problem, recursive problem. No, we are just telling you what is dynamic programming. Okay, dynamic programming also have top-down measure and bottom-up measure. Okay, there are two different measures for dynamic programming, and each one has its own way to do it. But right here, we're just teaching you the concept. The concept and the goal for dynamic programming is to simplify your larger case computing using your existing using the smaller case. So actually it's a streamline effort. Okay, streamline effort. Okay, so a classical example of optimization problem involve make change using fewest coin. Okay, suppose you're a programmer that for a vending machine. Your company want to streamline effort by giving out fewest possible changes for each transaction. Suppose a customer put in $1 bill to purchase 37 cents. What is the number? What is the smaller number coin that you can make the change? So your change should be $63. Okay. Then how can you make 63? You can use a 63 and all in pennies. That's not the smallest number, that's not the fewest number that you can use. So you will do 2 quarters, 1 dime, and 3 pennies. And how can we reach this problem? And they are also 2 cents or $2 bill. Okay, sometimes it's like that. So it's not always just 1 to 5. Okay, so this is actually, you need to study which one would give you the best solution, okay? So a greedy algorithm is to solve the problem using the largest dime or quarter first, okay? But that only work for US coins because you have apparently just in base 2 or base 10 or base 5 division, okay? If we do a number system that is not based on 1 to 5, then we will be in big trouble. The greedy algorithm will no longer work, okay? So if the amount does not match our several options, well, we want to do the minimum number of pennies plus the number of the coin. We should use minimum number of coins should be using 1 and plus the value minus 1 or 5 or 10 or quarter. So basically, your bigger case can use this different case to do it, right? Is that okay?
Yeah.
But this one, if you do top down, then you say, let's say you have a 63, you do top down, there will be 4 cases. Each one of them will 4 cases. So this one will end up to be order of 4n. That's a big problem. So we can do the other way. We can do minimum number of coins for 1, minimum number of coins for 2, and go up to 63. You should solve the problem, right? Right? Hello?
Yeah.
So basically, that is the different approach that you can use based on the idea. So this problem, okay, eventually how the coding is done, we don't know, but basically, look like this problem also bottom up would be better. Okay, so the algorithm do what we just described in listing 7, in line 7, whatever, okay. Let's see, right here, you have a greedy algorithm. Okay, let's see, the greedy algorithm, you solve the problem. And then we have dynamic solution. So dynamic solution is that you're 26, you have 4 cases, and you do coding tree like that. This is called memorization, it's top-down called memorization, okay? So here, this one, dynamic coin, you do here. It doesn't do recursion. You do the known result. Okay, you based on the known result, you actually have an array. So this is a dynamic programming approach. You calculate and you put your result into the known result and keep evaluating for bigger case. So this one is a dynamic programming way. It's a bottom-up way. Okay. So before we go into this detail of this algorithm, before we go into this detail of algorithm, let's actually go to the what is memorization. So gig to gig, this one dynamic programming, okay? So here it has a description for dynamic programming. So dynamic programming is an algorithm technique following the 4 property. Okay, it's very important based on optimization over recursion. Okay, as we know. The idea is simply store the data of the subproblems, okay, smaller case problems, so we do not have to recompile them, compute them. Okay, so that's the key idea. Most popular dynamic programming, including Fibonacci that we already teach you. Okay, so basically these different algorithms, when you do dynamic programming, you have to study each individual one. Okay, so right now we are not actually on it. So let's see. So here we have topic for interest. So there are 2 ways. One is called tabularization, one is called memorization. Okay, let's actually compare these 2 ways of dynamic programming. So there are 2 ways. Memorization is top-down approach. Tabularization is bottom-up. So these are 2 major approach for dynamic programming. This one very important, okay? Okay. So right here, look like, okay, up to here enough, okay? We just want to give you the idea. We don't want to go into there. We need to come back to our problem. So right here, this one is the example that we got is a dynamic programming approach. It is a memorization, it's a top-down approach. Okay. So top-down approach would be doing these. Okay, so basically, what you would do is that if you finish this one, you put it into table. You put into table. Since you put into table, so you do not need to re-evaluate. So if you say two Fibonacci, you say f of 5, you evaluate f of 4 and f of 3, right? These two, you don't have the data, so you continue to do f of 3 and f of 2 and f of 2 and f of 1. F of 1 had data, so you finish this one. Your f of 2 will evaluate f of 1 and f of 0. So you put the 0 and 1's value into there, you still have the value, you can do f of 2. So f of 2 also have the value. F of 2 have a value, this one you do not need to calculate because you already have it. You get a value from the evaluation, the known table. And then 3, you got a value from here, you also get a value here, you actually continue. Is that okay? So even exponential growth tree, you can use the table. I'm sorry, you can do memorization. So memorization is to keep the value of your previous evaluated result into a memory, and then later you can get it. Any question?
No.
If the value is a number or a string, you can basically put it into a hash table to do it. Okay. You can basically put it into an array or hash table to get it. It's an order of one access. That will save time. Okay, so that's no problem. That actually is okay. So let's see. Let's right now. That's actually just this is a technical memorization. Okay. So here, let's look at this one. I'll try to get a program. Okay, I'll try to program. If we do have it, then we just copy it over to look at this version. Okay, let me try. Okay, I did that a long time ago, so at this moment I have no confidence that we can get it right away. Okay, I know it buried somewhere. Let me just copy from here to the program. Okay, I'm sorry. Let's just do it. So right here, let me open a new directory. This one, let's call it change. Okay, not too bad. This one we can handle. Okay, it's not a problem. And copy the main program. Okay. Okay, let's start it from main program. We delete the wrong letters. So the so-called coin value, we have 1, 5, 10, and These are different test cases, I believe, okay, different test cases. Oh, I think that actually is the coin value. How comes the 21 and 25? I'm not sure, okay. Why there's a 21, 25? Maybe 21 is created just for example, okay. So they should not have a 21. Okay, we'll look at it later, okay. This one is questionable. Let me put a question mark. So the change you need to have is 63. We talk about it $100, and then you need to return 63 cents. 100 cents, okay? And then here let's delete the unwanted factors. So the known results initially is you actually 0 cents, you do 0, so you from 1 to 64, okay? Because you want to solve the problem for 63, so the known result is like that, okay? So you recursively call a function called recursive dynamic programming part, and eventually you get a result that would actually return it, okay? So right here, let's actually clean up the mess right here. Okay, so far so good. We actually finished the main program, clean up, and now we know it. Now next one is actually clean up for the recursive function. So we got a valid coin list and the change you want to get, and vector of the known result, okay? So we got that, and then here we have the minimum coin, number of coin you need to have, and the number of the coin you need to have, you can have. So eventually you will return the minimum number of coin. This is okay, we got it, okay. So in the middle, we start to do for loop. So this is for loop, we'll go to the for loop to, I'm sorry, I hit the wrong key. We'll hit the for loop from 0 to coin values size going to different coins size. Okay, so if any of the coin value equal to the change, you have exactly changed that's good enough, then your change value will be 1. Okay, these are actually not a problem. So your coin value equals the change, and you don't need to do anything, you just return 1. You just need 1 coin. This actually is no-brainer, not a problem. Okay, so this is no-brainer case. We finish it first. Is that your change is one of the coin type. No problem. This one, okay, we solve it. Next one is else if the known change greater than 0. So the change so far actually already has some value. If the known change already has some value, then you can directly return a known change value. That actually is also fine. This you already know what they are. Okay, so this is also a condition you don't need to worry about. So you already written that. That actually is also okay. Okay, if not, you actually continue to do the following. Your change is not the coin list. It is also not it is also not not known already. You go into evaluation, you will go to if the coin values y, you go to every possible coin value, and you go to every coin value if y less than change, this is equal change. That means you can use it if the coin value greater than change, then you cannot use it. You don't waste time. So each one of them, you do the kind of logic we use, the change minus the coin value, and then the number of coin will be the recursive call. So here the recursion right here, actually recursively calling a smaller case right here. This is a recursive call, okay? After the recursive call, you got the number of coin. If the number of coin less than the minimum coin you have, you need to update your minimum coin. Okay, you need to update your minimum coin. Okay, so you need to update your minimum coin, and then you also save your minimum coin to your known result of the change. Okay, if you have exactly change, exact change, then you will use it. Okay, so that actually is the result. Okay, so 1 plus that, so you have the number of coin and eventually store that. That actually also true. Okay, so this recursion actually is solved. Okay. So right here, we do still see a problem. Here, they still have some problem. Okay. Okay, so I think this one is ready to go. Everything okay. Let's do terminal. So C++, change the CBB dashboard change. Okay, so minimum is 3. Let's actually delete 21. We don't have a 21 coin, okay? So 21 coin deleted, we need to have 6 coin. So that 21 actually help, okay? That 21 actually help. So let's think about it. If we have a 63 and we have the 21, what can we do? We can do maybe 21 times 3, right? I think that's why there's a 21. Is that okay? Hello?
Yeah.
And then if we don't have 21, then we need to use quarters. So it's actually 2 quarters for 50. 1 dime for 10. and then 3 more penny, so that they should end up with 6 values. Okay, but anyway, this exercise, mental exercise, is good enough. Okay, so the 21, I believe that it is used because it will make 63 much easier. So with this coin list is very important. Okay, if you only have 1 file and this kind of value, that's fine. So if you can allow the special value, then this problem become a dynamic programming program. Okay, so if you don't allow 21, then actually you can use your 3D algorithm to solve it. Does that make sense? Your 3D algorithm just use the bigger coin first. That should solve the problem. But if you actually is allow some other number, then your 3D algorithm will not be the best solution. So when you do competition, you do need to know in what case you might need to 3D algorithm might not work. Okay, so in the bronze division, I think most of the problem can be used for 3D algorithm. But once you move into silver and above, it may not. Okay, it may not. Then you may need this algorithm. So right here, the key point is this dynamic programming part. How you actually know how to use the recursion and you understand. So as long as every situation you handle, exact change, okay, long change, okay, if these two you can guarantee, then you can use your recursion for any coin list that's smaller than change. You can try to use it and see what result it has. Does that make sense?
Yeah.
I'm talking about when you do recursion. You know the exact change work. You also know that if the case is known, you will use it. Then for the case of the unknown one, you try every possible coin and deduct the value. You should be able to find a recursive algorithm that will work. That's an easy dynamic programming approach. Is that okay? So this one, I just show you using the evaluation tree to solve the problem of coin selection problem. Okay, and give you an idea of using a simple vector of coin value and a simple vector of known result. So known result cover from 0 to the number. So it's an order n memory. But the evaluation tree, I think, can drop down to a runtime of log n time. Does that make sense? Hello?
Yeah.
That's the key. Okay, that's the key. Okay. Trade off the memory with the time. And here we only give you a very basic example of what is dynamic programming. Later we go into the more tree and more algorithm. Okay. Any question today? Okay,
No.
that's it for today. Okay. Thank you. See you next time. Bye bye.
Bye. Thank you.
Bye bye.